Hi everyone, this is lesson 2.7, Electrophilic Addition Regioselectivity. This is adapted from PSHS Chemistry 3 module lesson 2.7. If you would like to watch more videos like this, please don't forget to click the subscribe button as well as the bell button. For this lesson, we have two targets. First, to apply Markovnikov's rule in predicting the products of addition reactions, and second, to determine the reactants given the addition products. To start, synthetic organic chemists design processes by which compounds can be prepared in the most efficient way to yield the highest volume in the purest form attainable. If we would like to produce the product shown below, let's explain why substrate A is a better starting point than substrate B when preparing the required product. Notice that to produce the desired product, substrates A and B should also undergo electrophilic addition. For substrate A, the OH group may attach itself to either of the two carbons holding the double bond, which actually produces just the same product. On the other hand, for substrate B, when the OH group attaches itself to either of the two carbons holding the double bond, the end products are different. Only one of them is what is equivalent to the desired product. Therefore, substrate A is a better starting point than substrate B. To learn more about reactions like these, so we will proceed to the topic. Electrophilic addition of hydrogen halides, or HX, in alkenes and alkynes, which is called hydrohalogenation, is characterized by the formation of a planar carbocation intermediate, which was discussed in the previous module and also in the previous video. So in asymmetrical substrates, various carbocations may form depending on where the electrophilic moiety, or the H part of HX, attaches. So in this illustration, which was also shown in the previous video, you can see that a carbocation intermediate has been formed. Also notice that for this example, the substrate is symmetrical. If, for example, we would have an asymmetrical substrate, then the carbocation that would be formed would be different depending on whether the positive charge is acquired by the carbon on the left or by the carbon on the right, depending on the different branches or the different R groups attached to these two carbons. So the relative stability of the carbocation intermediate formed would determine the major product. So here's an example. Here we have three different structures. The first structure being symmetrical. The second structure also somewhat symmetrical, but it's not symmetrical along the double bond. And also the third structure is not symmetrical. So the variety in carbocations formed from a single substrate leads to variations in the products formed. Therefore, let us see what kind of carbocations are formed from the electrophilic addition of these different alkenes. Let's assume that they're going to be reacting with HCl. So the first step in the mechanism of electrophilic addition would be the attachment of the electrophilic moiety, in this case, the H plus, to the carbon, while the other carbon acquires a positive charge, thus making the structure or the intermediate a carbocation. So first, let's take a closer look at the first structure. So for the first structure, if the electrophilic moiety, or the H+, attaches itself to this carbon. So this carbon now becomes sp3 hybridized with 4 groups around it. The other carbon acquires a net positive charge, and this now is the structure of the carbocation. If the H+ attaches itself to the other carbon here, this other carbon would acquire the positive charge. And that's basically just the same as this structure. Therefore, in this case, we only have one possible carbocation. So for symmetrical alkenes around the double bond, then we only have one possible carbocation. On the other hand, if we have an asymmetrical alkene, notice that when hydrogen, or H+, attaches itself to either of these two carbons, different carbocations are formed. So if the hydrogen attaches itself here, then the other carbon acquires the positive charge. On the other hand, if the H+ attaches itself to this carbon, then we have the positive charge acquired by this carbon. Therefore, we also have a different structure of the carbocation. Also, for the third structure, also an asymmetrical alkene, notice that depending on whether the hydrogen, or H+, attaches itself to this carbon or to this carbon, so the opposite carbon, or the other carbon from the pi bond, acquires the positive charge, therefore producing a different carbocation structure each time. Now, these different carbocations being formed gives us an idea that we have a regioselective reaction. So this happens when a reaction yields predominantly, or if not exclusively, one isomer when more than one constitutional isomer is possible. So if these two carbocations are possibly formed from this reactant, then we would definitely form these two products. However, we expect that one product is favored over the other. That's because one product would be more stable than the other. And that is now called, this reaction is now called a regioselective reaction. Again, that is a reaction wherein one product, which is an isomer of the other possible products, is favored over all the other possible products of the reaction. Basically because in this case, the carbocation that is formed is more stable. So taking a closer look at the degree of substitution of the carbocation, so here notice that for this carbocation is a primary one because we have the carbon here and it's just attached to one other carbon. Then it has two hydrogens attached to it. Therefore, this is considered a primary carbocation. On the other hand, the other possible carbocation formed is a tertiary one. So this carbon, which has acquired the positive charge, is bound to 3 other carbons, therefore making it a tertiary carbocation. For a secondary carbocation, you may have guessed by this time now that it's bound to 2 other carbons here, and it's bound to 1 hydrogen. And then again, similarly, this tertiary carbocation has the positively charged carbon bound to 1, 2, 3 other carbons. So which carbocation is most stable? The trend is tertiary carbocations are most stable compared to secondary, primary, and methyl carbocations. Now, why is that? The module suggests visiting this video, so you may watch this video, but in a glimpse, carbocation stability follows this trend because of hyperconjugation. So from this illustration, let's take a closer look at the structure of this carbocation. Okay, so here's this is an example of a primary carbocation, and let us take a look at the orbitals comprising it. So for this carbon, we have a trigonal planar structure or shape around it and the empty p orbital. Therefore, this carbon has a positive charge. And beside it is this carbon with 4 groups around it. So it's already sp3 hybridized with 3 s orbitals overlapping or forming a sigma bond here, forming 3 sigma bonds here. So, okay, let's try to overlap these shapes on this structure. So there, it would look like that. So again, here's the trigonal planar part of the carbon bearing the positive charge with the empty p orbital. And on this carbon, we have the sp3 hybrid orbitals, 4 sp3 hybrid orbitals overlapping with the 3 hydrogens. And these, of course, are overlapping also with the s orbitals of the hydrogen atoms. So what happens in this case is that the empty p orbital here, as you know, is able to form sideways overlap with previously an empty p orbital also, with previously a p orbital here when this carbon was previously sp2 hybridized as well. However, because this has now become sp3 hybridized, therefore it is left alone. Still, is it possible for this to be a little bit more stable and not be left alone to contain the positive charge, or in this case, to bear with the emptiness and the loss of an electron, therefore having a net positive charge? So it is still possible, and that is through hyperconjugation. So hyperconjugation happens when this p orbital lies parallel to any one of these sp3 hybrid orbitals. In short, it just makes do with the available sp3, any one of the available sp3 orbitals here, because remember, this bond here, which is a sigma bond, can rotate. Therefore, while it rotates, there will be a point where this p orbital becomes parallel with one lobe here of an sp3 orbital. Now, if they are oriented parallel to each other, they may form a sideways overlap and share electrons. Therefore, this emptiness being felt by the empty p orbital may be relieved by its sideways overlap with an sp3 hybrid orbital from the other carbon. And now the 2 electrons which has filled the sp3 orbitals here may now travel to the positive charge here coming from the empty p orbital. Okay, now this is just an example showing a primary carbocation. So in a primary carbocation, the carbon bearing the positive charge is attached to one other carbon. Now just imagine if these two other sp2 hybridized orbitals are also bound to other carbons, which would probably contain also sp3 or other hybridized orbitals, which may also form sideways overlap with the empty p orbital here. So it may be able to form multiple pairs of hyperconjugation with the other orbitals coming from other carbons in probably a secondary or a tertiary carbocation, thus making the structure more stable because the excess positive charge is spread over a larger area, or in other words, because it's not the positive charge that's traveling, but the electrons. So more electrons are able to hyperconjugate with this MPP orbital. Therefore, the concentration of the positive charge is dispersed and the whole structure becomes more stable. Okay, so again, that is why tertiary carbocations are more stable than secondary carbocations, than primary carbocations, and the methyl carbocation. So notice that for a methyl carbocation, it's not the carbon holding the positive charge is not bound to any other carbon, and it cannot really share the burden with the hydrogens attached to it. So it bears its own MTP orbital. Okay, so going back to this reaction, we have already identified the possible carbocations formed by the electrophilic addition of these two different structures, asymmetrical structures. So, as a rule, the electrophilic addition of hydrogen halides, HX, and asymmetrical alkenes is a regioselective reaction which obeys Markovnikov's rule. So Markovnikov's rule states that when HX adds to an asymmetrical alkene, the H atom from HX adds to the carbon with more hydrogens initially attached to it, or the less substituted carbon. In this case, H prefers to be attached to the carbon that is less substituted. So this carbon is only attached to one other carbon. So it attaches itself to this carbon. And as a consequence, the positive charge is placed on the carbon with more substituents here. And then for this other structure, so this hydrogen would prefer to be placed not on this, the hydrogen would prefer to be placed to the less substituted carbon, that would be here. So it would be placed here while the positive charge is assigned to the other carbon. So as a consequence, the more substituted and more stable carbocation is formed. So these two, the tertiary carbocations, are formed. Again, Markovnikov's rule kind of focuses on where the electrophilic moiety attaches itself to, because that's the first step in the mechanism. So the electrophilic moiety attaches itself to the carbon with less substituents. So that would be, in this case, here, and in this case, here. Therefore, the other carbon would bear the positive charge, producing a more stable carbocation. Since the carbon that would bear the positive charge would be the carbon bearing would be the carbon that is more substituted. So let's take a closer look at the third case coming from compound 3. So compound 3 is able to produce 2 possible carbocations, and we've already identified that the tertiary carbocation is the most stable. Okay, now these 2 carbocations may form their corresponding products after the attachment of the nucleophilic moiety, which is chloride, to the positively charged carbon. So in this case, chloride attaches itself to this carbon, and for the other carbocation, chloride attaches itself to the more substituted carbon. Now this is the major product. Again, this product comes from the carbocation formed from H plus following Markovnikov's rule, attaching itself to the less substituted carbon. Thus, as a consequence, the positive charge has assigned itself to the more substituted carbon, producing a tertiary carbocation, which is the most stable type of carbocation. And now that positive charge attracts the chloride ion and produces this product. Now this is the major product of the electrophilic addition of this alkene. So in the electrophilic addition of HCl to 2-methyl-2-butene, the formation of product 3B, a tertiary alkyl halide, is favored over 3A, which is a secondary alkyl halide. So it's considered a secondary alkyl halide because the halide part is attached to a carbon, which is attached to 2 other carbons. On the other hand, 3B is considered a tertiary alkyl halide because the halide part is attached to a carbon attached to 3 other carbons. Again, this has been made possible because the electrophilic moiety has followed Markovnikov's rule and attached itself to the less substituted carbon, thus producing a more substituted carbocation, which is more stable and producing the major product after the nucleophilic moiety has attached itself to the positively charged carbon of the carbocation. So, not all electrophilic addition reactions in alkenes exhibit the Markovnikov rule or trend. Some exceptions would include the addition of halogens, X2. Of course, it's not going to follow Markovnikov's rule because both the electrophilic moiety and the nucleophilic moiety is just X. Also, in the addition of water through hydroboration oxidation, which exhibits anti-Markovnikov's rule. So in this case, these 2 reactions are exceptions to the Markovnikov's rule. For the Nav Gate part of the lesson, we're asked to draw the products for each of the following sets of substrate and reagent, and where multiple products are formed, identify the major product. So for the first reaction, we're asked to add HCl to this structure. Again, following Markovnikov's rule, remember that the electrophilic moiety, or the H+, would attach itself to the less substituted carbon, in this case here, and the chloride would attach itself to the more substituted carbon, in this case that would be here, producing this product. So Okay, here's the chloride attaching itself to this carbon, resulting to this product, and then the hydrogen, which has attached itself here, is not drawn anymore in the skeletal structure. Here's the other possible product in the anti-Markovnikov's orientation. So this is not favored. In the next example, we have a symmetrical structure. Therefore, H or Br may attach themselves to either of the two carbons and you'll just get the same product. Here are the other two items at the Nav Gate part. These are graded. So again, just remember that we are following the Markovnikov's rule for the reaction. So again, hydrogen would attach itself to the less substituted carbon, while bromine would attach itself to the more substituted carbon. Also, for this case, H would attach itself to the less substituted carbon, while OH minus would attach itself to the more substituted carbon. Since H here is the electrophilic moiety, while OH minus here is the nucleophilic moiety. So you're only asked to draw the products. So I don't think that the presence of the acid here would be any problem or would be unfamiliar to you because you're not asked to draw the mechanism. For the nut part, you're asked to supply the missing substrate and or reagent with the following compounds, with which the following compounds can be formed through electrophilic addition. So here are your desired products there. So you're asked for here the reagent for letter A, the reagent for letter B, the reagent for letter C, and here both the starting material and the reagent for letter D, and both the starting material and the reagent for letter E. So I would like to show again this table or a list of examples of the different reagents for electrophilic addition, where the electrophilic moieties and the nucleophilic moieties are described or enumerated. So for letter A, it's very straightforward, as well as for letter B and for letter C. For letter D, since this carbon in the original structure would be part of a double bond, so you'll just have to decide whether the double bond from the substrate would ideally be found here or there. Actually, this structure and this structure with the double bond here and here would be equivalent. So in this case, again, you'd also need to decide whether you would like to start with a structure with a double bond here or with a double bond here. That is all. I think that ends the lesson. Again, I hope that you have learned the lesson and the module better through this video. And again, if you'd like to see more videos like this, if you'd like to support my channel, please do subscribe and click the bell. Thank you, class, and goodbye.